Okay, just not
Number 1 should turn out to be 1/5. Number 2 should be -7/5 in the end. And then number 3 is that bottom line is all the way simplified. There could be a variety of different answers for number 3. That's perhaps the most simple, or one of the more simple versions of that. So I want to give you some time to look and think, reflect on how you're doing, and ask questions as needed.
Why is that not a number 3? Why is it not a product rule?
There's 2 product rules. So I've done some simplifying. So for number 3,
How we turn 1 over x times x cubed
x squared. Yep, so this is a product rule right here. And then this is another product rule right there. Yeah. Oh, yes, I did. On that one. That one technically no, but I would honestly say I think that it's actually faster, because if you think about it, if you solve for y, you have to subtract the x squared over, factor out the y, divide by -3x plus 4, and then do a quotient rule on that.
Because it's
So I think you have to admit that at the very least, we're even so here, is 3x is good implicit,
and then
that's
plus, you know, 2d1 just gets to x squared because it's 1 over x. So I'm writing 1 over x.
Okay, so just reflect on what you see, reflect on what you've got. You have to answer questions from you as they come up.
2d1 is x cubed over x, which is x squared. Like it's x cubed times 1.
It's best to simplify it before you move on. Definitely. Otherwise, you end up with this convoluted quotient rule that still would be fine. But
Well, she was just confused because you were like simplifying.
I simplified pretty fast. Yep. Mitch, go ahead.
Where did that plus one come from on 2?
Where did the plus? So you're talking about. Oops. You're talking about this right here.
Yes.
Okay, so this, I'll highlight this in red. This right here is a product rule. And so what I did with this is I said that it was essentially -3 times xy. And I called the x my 1 and my y my 2 on the whole 1d2 plus 2d1 thing. So then to do a derivative of that, I said -3. And then here I'm going to do my 1d2 plus 2d1. So here's 1 d2 plus 2. What's ddx of x? And I chose to just write y times 1 as y.
Okay.
But if you write y times 1, of course that's fine.
Can you walk through number 1 real quick?
Say again?
Can you walk through number 1?
But
Sure.
really quickly on that one,
Yeah.
can't you just count -3x as your 1?
Yes, you totally could. Yeah, there's a wide variety of things you could do. Yep. And that would, some could debate that they like that better. And I'm fine with that. Okay, let's walk through number 1. So how in the world were you supposed to know that number 1 was dealing with inverse functions?
F of g of x equals x.
Yeah, and the truth is, to be honest with you, even if you didn't look at this and say, oh, it's an inverse function situation, you could actually derive the formula with that, couldn't you? So I think there was a number of ways to arrive at where you want to arrive. But the bottom line is, whether you develop it or you just think to yourself, oh, that's a key indicator of inverse functions. However, whatever thought process you use, I would want you to get here where you say g prime of x equals 1 over f prime of g of x. So it's an important step, right, to recognize that this means that they are inverse functions. And then you could arrive at that formula, or you could just redevelop it, whatever. So then we're looking for g prime of 11. So g prime of 11 would be 1 over f prime of g of 11. Right, wherever we see an x, we just put an 11. But then you really, if you're real honest about this, you run into some pretty significant issues trying to figure out what in the world g of 11 is, right? Because there's no function for g. And even if you recognize that they are inverses, there's no way to explicitly find the inverse of f. And so you're kind of stuck until you come up with the idea, or you remember the idea, that an input for g is the exact same thing as an output for f. So I'm going to just use that and say, to help me evaluate that, I'll say 11 equals 1/4 x cubed plus 2x plus 5. And this is that curious moment that I mentioned last time where you're going to have this equation here, and more often than not, you're not going to have a calculator. You're going to have like a table or maybe a graph or just an expression like that, and you're going to have to just use some brief mental math to figure this out. So you start guessing and checking, and you don't start guessing and checking with like 1/17 or 9/31. You start with what? 1 or 3, or in this case, 2 works out really nicely, right? If you say 1/4 of 2 cubed is 2 plus 4 is 6 plus 5. Oh my gosh, it worked, right? So we arrive at this and we say, well, if that's true, then x must equal 2, which means that this equals 1 over f prime of 2, because g of 11 is 2 based on what we just found. And then I would just use the derivative, which I have written above there. You kind of can't see it, though. I'll write it off to the side. F prime equals 3/4 x squared plus 2. You drop a 2 in there, you end up with 3/4 of 3 is 3 plus 2 is 5. A little arithmetic, you get 1/5. Grant, I feel like somewhere in there you totally got it. Am I right?
Yeah.
Okay. Any follow-ups on that one from anybody? Okay. Finally then, what do we haven't talked about 2 yet? We talked a little bit about 3. Anything else? Yeah, Ty.
Can we talk about 2?
Okay, what about 2?
I just don't necessarily. I kind of confused about the dy over dx part again.
Get confused about the dy over dx?
No. Yes and no. Can you just walk me up to the part where, like, tell before you evaluate it? Because I understand like evaluation stuff.
Sure. Okay. So this might be. So there was a couple of folks that, as I walked around, were still kind of struggling with the idea of an equation that is defined implicitly. And in all those cases, folks were wanting to put equal signs in just kind of like wherever. There's one equal sign in this, and it's already written. So for us to like introduce more equal signs would not be correct. So I've seen people over the years a lot that want to write something like this. Check this out. Maybe you were tempted. Watch. Do you see how somebody would be like, they would really want to do this? Why would someone want to do this? Isn't this what you've always had? You've always had an equation that has been defined explicitly. So if you couldn't write it as f of x equals, it's like you're just like stuck. Like I've never seen it done this way. This is defined implicitly. I mean, there's just no, well, there is a way around it on this particular one, but in many cases, there's just no way around it. And so we can't just introduce like this whole other equal sign and call something that's not a function of x, because there's y's in there, a function of x. We just can't do that. And so if we are looking for the slope of the tangent line, or in this case, slope of the normal line, I'm just going to take this for what it is. It's defined implicitly. So the way that I'm going to find a derivative of it is to use implicit differentiation. So if I am trying to find dy dx, that means that I need to do ddx to everything. That's the derivative with respect to x. So ddx of x squared, 2x. That's just how it's always been. But then we start to get into these other terms that have y's in them. And that's where the chain rule factor is going to be something other than 1, because right there the chain rule factor was 1. I'll do this Ben's way. I'm going to call negative 3x my 1 and I will call y my 2. It's a little bit different than you'll see on the solution up there, but it's just as good. So I got to do a product rule, right? So here's 1. What's d dx of y? dy dx. So here's my 1 d2 plus 2. What's d1? Just -3, correct? Yeah, so d dx of -3x just be -3. And so I'm done with the product rule. I move on to the next term. What's d dx of 4y? It's 4, right? And then we multiply by the chain rule factor, so it'd be 4 dy dx. And then how about d dx of 6x? Just 6. So what follows is essentially my effort to get the dy dx all by itself. So this is, I'll put this in quotes, this is just algebra. That doesn't mean it's easy. Don't get me wrong. We're just rearranging this equation. Now we're trying to get the dy dx's all by itself, the dy dx all by itself, and all the other junk on the other side. So my first step would be to get the 2x and the -3y over there. So that's going to be 6 plus 3y minus 2x. And then over here, it's going to be -3x dy dx plus 4 dy dx. And this is the step that sometimes people forget or they mess up. What's my next step? Factor it out. There you go. And factor out, and then what's the last step? Divide. And there, now you're to your plug-in point. Make sense? Cool. All right. So keep thinking about questions. While you're thinking about those, I want to just talk to you real briefly about tomorrow. Who are my 2 drivers for tomorrow? Joey, Allie. Okay. So drivers. At the end of class, I'll throw the picture back up there of all the teams and groups and all that stuff. What you guys are going to want to do is you're going to want to talk to your teams and say, when class starts, meet me at the front of the school. I'll pick you up in my car. Or meet me in the parking lot at my car. I always park by the light pole, blah, 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 whatever. Meet me there. And then once you have your whole team, go to your spot. Good? My police. Who are my police? I forgot. Reed? Aaron. Okay. Same kind of thing. Okay, so you guys are going to want to, you'll look at your teams again. You want to connect with them real quick and say, meet me at the front of the school, meet me in the front of the arts building, whatever, wherever you feel is appropriate. Arrange that. And then tomorrow, once those people have joined you, go to your spots. Make sense? Okay. And then really, like I said, there's not going to be a lot of revealing of anything yet. Like that's kind of all you need to know because the drivers know what they're going to be doing. The police know what they're going to be doing. And then by the end of class tomorrow, we'll have it all wrapped up. And we'll turn the lights all the way on. Right now, it's still really dim. I get it. I totally, totally get it. Don't worry about it. It'll be fun. Because it almost always is super duper fun. In fact, I think it always has been. One note. Tomorrow's supposed to be a little bit cooler, like in the 60s, instead of like the mid-70s, like today or whatever. We should be fine. You're gonna be in a car in one form or another. So, whatever. Should be okay. I know it's a mystery. And Ty, we need to get you. There might be a couple folks that haven't been assigned to anything yet. We'll get you assigned. Okay. You all good? Did you think of any other questions on this? What we've been talking about? Okay, so guys, hey, listen up. Listen, please. We're going to transition, but I wanted to let you guys know a couple things for this week. Today is our final day in Unit 2. We're going to get this wrapped up today. Should be pretty comfortable. Tomorrow, we technically start Unit 3, but because we're doing a project, you really don't have to have your Unit 3 packet with you tomorrow. Wednesday, you do. So make sure on Wednesday you've got your Unit 3 packet ready to go. Our second quiz for Unit 2 is this Friday.
It's Thursday.
Well, so you guys know we have the college fair thing on Thursday, right? So we have a jumbled up schedule on Thursday, Friday. So we actually have our class. Normally on Thursday, it's actually going to show up on Friday this week. So we'll just call it day 4 of our class schedule this week. So that's over Derivative Skills 2. All the same stuff we've been doing. It's basically like all the derivative things we've been doing. And by the way, for the whole rest of the year, you will not learn any new derivative skills. We'll apply derivatives a lot. We'll do things with them and, practical situations, different situations, but no more new skills beyond today. So Any other thoughts or questions? We'll get into antiderivatives and all that stuff later.
One more question.
Yes, ma'am.
Sorry, on the second derivative for number 3,
Yeah.
when you do the product rule for ln of x times 6x, why doesn't it become 1 over x?
Well, it definitely does. So you're talking about coming off of this, and you're referring to this here, right?
No.
No.
The second derivative. Talking about the same part, but the one under it.
Well, I've already
That one.
I've already found the second derivative at that point. Going from here to here, I'm just simplifying. Like these two expressions here and here, they have the same value exactly.
Okay, so then I guess I am talking about the first one.
Okay. So it's there. I just did some simplifying on my way there. So let's just focus on this.
Yeah.
ddx of ln of x times 3x squared. So here is 1 d2, which you see right here, right?
Yes.
Plus 2 plus 2 d1.
Yeah.
What's
You just cross out the x's.
Yeah, it said x squared over x. I just instantly am like, I don't want some
Yeah.
crazy fraction in there. I just said 3x squared over x is 3x.
Gotcha. Cool. That's what I was saying. Thank you.
You bet. And I would say that's a pretty common theme, and this will be a theme throughout the year. It's not that I'm afraid of fractions, but if I can find a way to not have a fraction in there, I'm going to find a way to not have a fraction in there.
Yeah.
Sometimes they're going to be unavoidable. But if I can avoid them, I'm going to avoid them.
Is there like a word for like having a phobia of fraction?
Fractionophobia. Maybe there is. There's got to be one, right?
There has to be one.
Gotta be.
There's one for like long words.
Yeah.
And it's like 37 letters long.
Of course it is, right? You're afraid of the word describing it.
Yeah.
Love it. All right. If you guys would flip ahead to where we're going today. Thanks. Okay, hey guys, listen up. Hey, we spent a few more minutes on questions than I originally intended, and I'm fine with that. But that means that we need to be focused to finish up what we need to finish. So our final derivative skill of the year, not semester, of the year, final derivative skill is right here. We're going to be looking at finding derivatives of inverse trig functions. So you guys know that arcsine is inverse sine, arctangent is the same as inverse tangent, right? Okay. So in order for us to do these, we need to establish some ground rules. The first one is that A, as is typical, stands for a constant, like 7 or 3 or negative 13, some number, right? And that U stands for a function in terms of x. So it could be really, really simple, like just an x. It could be e to the x, it could be cosine of x, it could be ln of x, it could be square root of x, it could be any function in terms of x. Simple or otherwise. Make sense? So what I'm going to do is I'm going to list these off for you. I'm going to prove one of them to you, and then we'll work to apply these. Okay? So we're really only going to focus on 2 of these. I put 3 of them up there just because I thought you might be curious. We're going to be focusing on the first one and the third one. Okay? So the derivative of the inverse sine of u over a, again, u is a function in terms of x, a is some constant. Here's what it looks like. It's u prime over the square root of a squared minus u squared. Does that square root of a squared minus u squared remind you of anything you've seen in your past? Oh, good. Good find. Pythagorean theorem. That'll be important in a second. Let's focus on the third one. The derivative of arctangent of u over a equals u prime times a divided by a squared plus u squared. So notice with the derivative of arctan, there is no square root in there. Arctangent is plus. And oh, by the way, does that denominator also look sort of like the Pythagorean theorem? Yeah, some just different form of it. Yeah. So notice there are some similarities between these two, and obviously there are some differences. Anybody want to just venture a quick guess as to what the derivative of arc cosine might be? Yes, it's actually just the negative of the derivative of arc sine. We'll be focusing on the blue ones, not the purple one. I throw the purple one in there because every now and then WebAssign will just randomly throw in an arc cosine. So I thought I'd at least put that in front of you. But we'll be focusing for our purposes on, say, the AP test or any of our quizzes or tests, we'll be focusing on the two blue ones. Okay. So at this stage of the game, you're kind of in a position where you're like, oh, I guess I believe you. But let's prove one of these. Okay, I'll just prove one of them. Of the two blue ones, which one do you want to see proven? Arc sine? Okay, let's do arc sine. So here's how we do this. We're going to start off by writing this as an equation to kind of help us. And you'll see why this helps us here in just a second. We'll write y equals arc sine of u over a. And if that's the case, would you guys be okay with our goal being find dy dx? Does that make sense? Okay. So as that's written, that's what we're going to try to find. Of course, the truth is, even though you just saw it up there, we're pretending like we don't have a clue what the derivative of arc sine is. And so it would be better for us to rewrite that equation instead of explicitly, write it implicitly. So what could I do to write that implicitly that would maybe be a smart form? What could I do? I'm not sure what you mean by u. Well, no, I can't do the derivative yet because I don't know the derivative of arc sine. I got to rewrite this in a way that helps.
Sine of y equals u over e.
He's just doing the sine of both sides. That's actually a pretty smart move. So if I did this, check it out. Sine of both sides, sine of y equals, doesn't the sine of arc sine just cancel out? So I would just get u over a. Why would this be useful? Don't I know the derivative of sine? Yes, I do. So this would be pretty useful. I do want to point out one other rewrite that would be helpful. For those of you guys that tend to fall right into the quotient rule trap, let's remember that a is a constant. So I could rewrite this to be 1 over a times u prime times u. That makes sense? This will help me avoid that quotient rule trap. Okay, what was our goal again? So if I'm trying to find that, what do I need to actually do to my equation?
DDX.
I need to do ddx to that. So I'm just going to go parentheses, and I'm going to find the derivative with respect to x of all that stuff. And if you think about it, isn't this just implicit differentiation? Well, we've been practicing for the last week or so. So what is ddx of sine of y?
Cosine of y times dy dx.
Cosine of y, because the derivative of sine is cosine, right? But then since we're doing ddx of a y variable term, the chain rule factor will show up, and it will be this. And believe it or not, we actually did this last week. If you'll take a look at the back board by Ty and Bex there, that's left over from last week. So we've actually done this before. Hopefully you're seeing the consistency in this. Okay, so then what's the ddx of 1 over a times u? So it is, sure, 1 over a, but then we're doing ddx of a u. So you could write it as du dx or u prime. Yeah. So it'd be 1 over a times u prime. And again, we don't know how complicated u prime is, or how complicated u is for that matter. U could be super simple. It could just be an x. And in that case, wouldn't u prime just be 1? But it could be a lot more complicated, right? It could be cosine of x, sine of x, e to the x, ln of x. It could be all kinds of stuff. So we just put u prime out there as basically saying it's the derivative of whatever u is, simple or otherwise. Okay, remember our goal is to find dy dx, and there it is. Do you see it?
Yes.
Okay, so dy dx, I'm just going to do a little bit of algebra here. I would write this as u prime over a cosine of y. I'm getting that by just dividing both sides by cosine of y. and we feel like, yay, we're done. Except we're not, because does that look like what we have up there? It does not. Question.
Why wouldn't you do product rule on 1 over a times u?
Because a is a constant, making 1 over a constant multiple.
Oh, that's right.
The truth is, you totally could do the product rule, and as long as you handled the fact that ddx of 1 over a is 0, you would get the exact same answer, but I would suggest doing it that way. Okay, so then, what's the awkward thing that doesn't fit in our answer at this point? Cosine of y. So remember how earlier you all said, hey, some of that stuff looks like the Pythagorean theorem. Maybe we should try to use a triangle to help us deal with the cosine of y. So here we go. Here is a triangle, and it's a right triangle. I'm going to call this angle right here angle y. Can you guys think of any of the sides? What would some of the sides be if that's angle y? Based on all the stuff we have. Say again. The opposite would not be y. I think you're just misspeaking. The angle is y, right? Because it's cosine of y. And it's sine of y. Yep, so the opposite side would be what? Say again? It'd be u, wouldn't it? Where are you getting that from, Brendan?
Just the, I don't know, sine y equals.
I think this is what you were looking at, right, Allie?
Yeah.
So if sine of y equals u over a, wouldn't the opposite have to be u? And the a would be the hypotenuse, yeah. Maybe you're starting to see this. I got to do the cosine of y. So don't I need an adjacent side? I don't have it. What could I use to find it? Pythagorean theorem, which ends up giving us this. Right? You'd have to use the a squared plus b squared equals c squared thing to get that missing side. And now you can really start to see it. Now I can come back here and say dy dx equals u prime over a times my adjacent side over my hypotenuse. And look what happens to the a's. Bye-bye. Yep, they cancel out to be a 1. I end up with, oh, look at that. That's what I wanted. It worked out nicely. Okay, so I show you all that for a couple different reasons. Number one, so that you don't think that I'm just making this stuff up, or for that matter, your book is just making things up, right? There should be a logical reasoning process to get to wherever we get to. So, number one, hopefully you now a little more believe that that's true. Number two, I hope then that you could see how you could do a similar type of an idea to get to the derivative of arctangent of u over a. It would involve a triangle and some implicit differentiation. It would look a little different because the answer is different, but same process. Final thing is this. I hope that I have convinced you implicitly that it would be better to memorize these relationships for quizzing and testing purposes than to think, yeah, I'll just develop it. I'll just remember it by, going through some steps. In the middle of a quiz or test, this will take you 5 minutes if you're fast, 10 minutes realistically, and now like half your quiz is over, and the only thing you've done is derive the formula for the derivative of arcsine. You haven't even done it yet. You just found the formula. So have I convinced you that it would be a good idea to memorize these? And you're all probably good enough to just, if you wrote these down like 5 times a day for the next couple of days, you probably have them memorized for the whole year. Or if you made little flashcards and flashcarded yourself for a few minutes a day for the next week, you'd have them solid, right? If you just sit there and you do nothing, you won't have them solid. So consider your strategy what you'd want to do. Okay? The reason why I say that is because this is one of the few moments in our class and really the AP test where once you have these formulas down solid, it's sort of a plug and play. Like if you just figure out what the U is and what the A is, you just plug, done. Moving on, next one, plug it in, and done. So it's a formula, right? It's a recipe. So this is kind of like how many of your other math classes have been throughout the years. Memorize something and just drop some numbers in and you're good. And to this point, we really haven't operated that way at all. Hardly ever. So this is one of those moments where we kind of revert back to that old way of doing things. So if you would, please look at numbers 1 through 4. I'll show you some answers in a couple of minutes. See if you can use these relationships to figure out some derivatives. You can think of this as the good old days or the bad old days, however you want. So there they are, 1 through 4. Please try them out.
Oh, it's
A squared minus U squared. So you had that right in the first one. There's a variety of simplifying that can be done on 3, none of which are mandatory. So yeah, so it was almost like D over dx. D over dx. D over dx is, yeah, so I would, yeah. You really can't write dy dx either because you never call it y. You could just say, notice how I didn't write anything like that either. I'd be really careful about inventing out. Like there wasn't something that I always says there is one. Because you don't know